Good morning, almost afternoon. I'm glad everybody had a chance to go get your lunch. Now, if you have folks that will probably be a little bit more attentive since you have something in your stomachs you guys are eating. In any case, my name is Bill Geyer. I am the traditional helicopter maintainer, and I guess show of hands, who's flying a helicopter with RG Pilot? About 4%, maybe five. Yeah. Very few. In any case, great platform, and here it's been about probably 2 years now since two conferences since I've actually presented anything. Coming back to give you an update on what's been going on with traditional helicopter, and so there's kind of a laundry list of some things that we've been doing since the last time I briefed, and the big one's been kind of the auto rotation and trying to get into having like this assisted auto rotation, which if folks don't know, that auto rotation is a helicopter's way of gliding with power off. That's been kind of a big thrust over the last few years. So there's manual auto rotation, which Ferruccio and I want to step back for a second. I want to recognize Ferruccio Vicari from Italy. He's my co-maintainer for traditional helicopter. I also like to recognize and thank Matt Keir and Pete Hall for their work. They've been instrumental in helping out and getting furthering the code base for traditional helicopter, making it more efficient in that thing. So thank you very much. Manual auto rotation went in, and this basically just had added some parameters that made it possible for doing bailout more effectively and being able to set up for manual auto rotation. I'm going to talk about blade pitch logging. I'll talk about the direct drive fixed pitch tail rotor thrust linearization that Matt Keir worked on. I'll go over, many of you may not know that there is a helicopter auto tune that I wrote. So there's some improvements that have been done on that auto tune. Plus I have a few tuning tips that I add at the end. I'll go over this inverted flight feature. It's not a mode, it's a feature that allows you to invert the aircraft in a stabilized mode or another mode and fly the aircraft inverted. So I'll go over that. And then there's the new axis options for system ID that allow you to sweep the position controller variables to basically evaluate the position controller from a frequency response standpoint. Some of the current projects that we've got going on, Methodic Configurator, Amilcar Lucas, and Alistair Schreiber. We're kind of keying in on that. I know Amilcar has kind of been a big proponent. He's the one that designed that tool. So we're trying to reconfigure it to make it applicable to helicopters. And so that's kind of ongoing. Again, I said rotation's kind of been a big thing last few years. So I know Matt Keir and Ferruccio are going to be talking about assisted auto rotation. Over the summer, we had Astik Srivastava, who was a GSOC student who did this system identification wood tool. I will hopefully talk about that on Sunday. We'll see if we have time. And then I've been working recently a lot with Pete Hall on this Argicopter analytic tuning web tool that I'll be briefing that tomorrow. All right, so as far as blade pitch logging, so this is new that Matt Keir had added in order to basically track kind of what is the actual collective and cyclic blade pitch on the swash plate that the blades are seeing. About 2 years ago, I actually added the ability for the actual code or for the controller to know what the collective blade pitch was, only to make it easier and have less problems with users not setting up. We had this parameter that kind of told the controller where to kind of go no lower than this for the collective when you're on the ground. And that was a real difficult parameter for those users to set. And so to make it more convenient and kind of have a reasonable default value, I added the ability for the controller to know what the collective blade pitch angle was. And so Matt just took it one step further and it was able to have the cyclic blade pitch also determined by knowing the servo positions and then being able to be able to derive that from the servo positions. And so he added this it's essentially logging only. There's no really not being used at the moment for anything in the code for the cyclic blade pitch. But you can verify that with that parameter HSVMan you set that to pass through, and that allows you to verify what your collective and cyclic blade pitch numbers are before you go fly. And then when you log it, then you can kind of come back and see how much. Actually, it's very convenient for those that want to look to see how close you're getting to your control limits during a flight. So it's pretty useful. Direct drive, fixed pitch, tail rotor thrust linearization. So those of you that don't know, like we have several different tail rotor capabilities. So there's the servo, that's just basically the tail. It's a shaft driven tail rotor. It's driven off the main gear, or maybe a belt driven tail rotor. And so that servo just basically changes the collective pitch on the tail rotor. Then there's the direct drive, which is essentially like one arm of your multi-rotor turned sideways, right? And that it's a fixed pitch prop on there, and you're basically just changing the speed of the motor to make the thrust different. And so we never had any type of thrust linearization on there previously. And so obviously you can imagine there's fairly good nonlinearity between the thrust that's being produced based on the throttle position, because throttle is essentially RPM and thrust is a square of throttle. So that probably created some problems for the folks trying to use that type of a tail rotor, and created problems for the control of that kind of a tail rotor. So Matt Keir and I worked together. We got the DDFP in there, and I think Ferruccio was able to test it for me. But basically, it capitalizes off of what Leonard has in the motors library already. Pete brought it up to a common level that we're able to use it for both heli and multi-rotor. And so basically, it adds those parameters like thrust expo. It adds spin min, spin max to the heli parameters. And then we did the voltage compensation, which is a big win. That way, you basically get, for a given RPM, you get the same thrust regardless of the battery throughout the flight. So I thought that was a big win. Probably really improves the ability for the flight controller to more predictably control the tail rotor. So this is inverted flight feature. So Tridge had developed the inverted flight feature or implemented it about, I don't know, gosh, it's got every bit of 7 to 8 years ago. And at the time, this is a cool feature because it basically allows the user to, in stabilize mode, in auto mode, in any mode really at that point, to essentially flip a switch and the aircraft goes inverted and its controls do not change, right? Basically, raising the collective still causes the aircraft to climb, lowering the collective still causes the aircraft to descend. Now, some advanced RC pilots might not like this because, right, they're used to like, hey, I go inverted, I'm lowering the collective in order to hold to hover. But this makes it nice for new users or folks that will just want to have fun doing inverted flight. And so the big issue, though, with the original implementation was the loss of altitude in the transition, and so it was quite significant, probably 50 feet or so or more. And so basically, one of the things that we knew about but never implemented was this copter lean angle compensation, right? So this is kind of a big win on two fronts, not only for the inverted flight, but also for just normal flying in stabilized mode, where the controller is getting helped with the lean compensation, is helping the attitude controller basically, or I should say the altitude controller, to basically manage the thrust being put out to basically maintain level flight or altitude while you're flying. And so basically implementing, again, capitalizing off of what Leonard and was already in the copter code, we implemented into the heli side and was able to take advantage of this. Now the aircraft loses less than a couple of meters in the transition. and then again gains the fact that it's able to get some lean angle compensation while it's flying in stabilized mode or any mode that utilizes the stabilized controller. So alt hold, auto, all those modes. One thing about when you're setting up for this type of this feature, one thing to remember is, right, you got to set your aircraft up for 3D flight. So you want to have at least enough negative collective pitch so that the aircraft can hover inverted. And then the other thing is that the way this is designed, it basically just inverts the aircraft very quickly. I guess it just changes by 180 degrees the roll axis. So basically, if you don't have any rate limiting on the roll axis, what will happen is that the attitude controller will get way ahead of the aircraft, and you might have some unexpected behavior. So it's very important that you dial down the rate and add in a rate R max, and make it whatever your aircraft can do. You can kind of do some back and forth lateral stick inputs and see what the max rate is the aircraft can do. Basically just put that in there for the max rate limit, and that way, if it's 120 degrees per second, that's probably decent. Sure, it's going to take 3 seconds for it to or a second and a half to invert, but that's fine. It should be fine. So as you can see, Ferruccio flew this, and you can see that works very well, and I think he had a lot of fun doing it. All right, so off to HeliTune, auto-tune improvements. So a couple of things that were done with helicopter auto-tune. First, I'd already started working on kind of an angle P improvements to tuning the angle P tune or gain. And then, so that was back in 4.4. And then recently, I got the itch to kind of really try to improve the feed forward gain tuning. If anybody has done this, they'll know that the feed forward gain tuning was basically kind of, if you're talking about in the pitch axis, it would go down to 20 degrees nose down angle. It would then go to a 50 degree per second rate on the way up to 20 degrees nose up, and then it would come back to level. That was the old way that it was done. So I knew that folks with larger aircraft didn't really care for that because it was a little scary because of those large aircraft. Plus, the larger aircraft may have a tough time getting to that 50 degrees per second very quickly. So I improved that. I also went and looked at the max gain determination for rate P and rate D tuning. Changed how that chirp or that frequency sweep is done. We'll talk about that really quickly. And then kind of the big upshot of all of this was I really went through the code, and back when I coded it up originally, there's a lot of inefficient code in there, and so I really went through and I was able to save 5K in flash savings through doing all this update. So the angle P tuning and how I improved that. Basically, previously for angle P, I was just basically looking at the attitude frequency response. It looks at the attitude compared to the input attitude or requested attitude, and looks at like kind of the peak at the frequency where it peaks, and then adjusts it so that it doesn't go above I think a user specified value, right? Normally I told them that, hey, don't make it go above maybe 2 times. You don't want to have the response be twice the input request. But in some of the research I've been doing, looking at handling quality specifications, it's became like a better idea of looking at it from a disturbance rejection standpoint, because really the angle P controller is primarily helping out with a lot of angle disturbance rejection. And so there's a manned helicopter handling quality specification, Aeronautical Design Standard 33. It was developed by the U.S. Army. It's been around for years. They now recently updated that to a U.S. Mill Detail 32742 that is also out there. And they basically, what they're looking at here is, and what I used to tune the angle P was, hey, how much overshoot do you have in the disturbance rejection, right? When the aircraft gets hit by a gust, how, in its correction for being hit by that gust, how much is it going to overshoot in the response? And so that's what this is basically looking at in a nutshell. And the criteria is no more than 5 dB, which is about like 1.7 times the input request. or the disturbance. And so that's, without going into too much detail, that's essentially what I changed that tuning guide to in order to tune the Angle P controller. All right. So the next thing was the feed forward gain tuning. Like I said, that original design of that feed forward gain was to get it into a constant rate, either in roll or pitch or yaw, and then try to determine, hey, what is the feed forward gain required to achieve that constant rate? But I've decided that I could probably do this with a low frequency dwell. And so I went and implemented this low frequency dwell. It's a quarter of a hertz dwell. Here, Ferruccio again is provide some video here to show how this works. And this is a roll axis tuning. And you can see for helicopters, really highly coupled between pitch and roll. And so you'll see a lot of kind of motion in the pitch axis as well. It almost looks like it's toilet bowling as it's doing that back and forth motion. But again, this allows the auto tune to then look at the response and be able to determine what that feed forward gain is from that response. For max gain and the rate P and rate D tuning, those gains, rate P and rate D, it originally was a rate-based sweep, meaning that the frequency, the chirp was done in rate, angular rate. So 50 degrees per second was what it's looking for. And that kind of gets scary because as you reduce the frequency, like I always started at about 10 radians per second or close to 2 hertz. But if you went less than 10 radians per second, well, if you integrate that 50 degrees per second, right, that as you go slower, the aircraft has more time to increase its attitude as you're doing at that lower frequency, and so it kind of gets a little scary. And so it wasn't good for larger aircraft where you had to go to lower frequencies. And it just from the experience I had, I knew that I could get away with just doing an attitude-based sweep. That then I could look at pick off certain parts of the code where I could get my target rate and resultant rate and be able to then do the analysis on that. And so yeah, I used the system ID mode chirp generator, and then was looking at the attitude. Did it based on attitude inputs. And again, that says attitude controller feed forward disabled. That's basically the recovery roll, recovery pitch type inputs for SysID. It uses those because it basically gets rid of the input shaping and helps the controller look at the natural response of the aircraft. Okay, some tuning tips for folks that may be tuning their helicopter. One of the biggest challenges by AutoTune for being able to tune helicopters is trying to deal with these lightly damped modes that the rotor essentially is really causal for. And so what happens on the left here, you see that I'm showing a response, basically the bare airframe response, and you can see that it's flatlined here. It's almost 0 degrees for a rate command, and so it basically means that helicopters are naturally rate command systems, right? You put an input for a bare frame helicopter, you're going to get a rate response, whereas multi-rotors are acceleration command, and that's why they're so difficult to fly without any augmentation. So here, the biggest issue here though is at some frequency, I start seeing this peak where I see this 6 dB rise. It's like twice the output as compared to what I requested, right? But this is, like I said, this is like the unaugmented aircraft. So now if I go down here and I look at where I have the rate controller, and so now I've set my feed forward to kind of so that I could match the output rate matches my requested rate. Now I still see this 6 dB rise, right? And so now when I try to add any type of P gain or D gain, P gain especially, that just gets higher, right? That peak just gets higher. And so how do you deal with that? I found 2 ways that you could deal with that problem. First is, so in the left here now, I've added some P and D gain to kind of show what happens to the response in the orange. The original response is shown in blue still, but the response in orange is what I did to kind of say, well, let's go ahead and tune this up I added some P and some D. You can see now I got close to a 10 dB rise, or like a 2 point, I don't know, 2.8, whatever that would be as a ratio, but a fairly large overshoot, right? Almost 3 times the requested response is what I'm getting as an overshoot. So how do I deal with that? Well, one way I could do that is just for helicopters, that ringing or that response where I get this overshoot could be either uh, it's mainly on the attitude loops that it's getting or that it's excited, right? And it doesn't matter whether it's the pilot that's doing the input at that frequency or the controller, the attitude loops that do that input. Either one's going to excite that frequency and cause this response. So I'm able to actually use the target, the low pass filter on the target. This guy right here, FLTT, I put that as 2 hertz, right? Very low, right? Very low. But what it does is it basically shaves off that peak and kind of gives you a nice, better response so you don't get that overshoot that's occurring. But the impact of that is you may suffer a little bit of phase, your phase may be a little larger phase lag. For most folks flying, pattern work or, generally doing some work where you're not in large, high disturbance, it may be okay to be able to tune that way and not have to be a very optimal tune. That's okay. I found it to provide satisfactory results for those kinds of situations where you're not in like a very dynamic, turbulent environment. But if you really want to, so thanks to Andy Piper right up front. He helped implement the PID notch filters. And so the PID notch filters opened up a new way for heli to basically be able to kind of calm down that overshoot. And so again, same plot on the left showing the 10 dB rise, but now I added this target notch filter right on the target. And I set it to the frequency, which is around 4.5 hertz. Q's a little bit wide, right? I've kind of flattened out the notch. It's a fairly wide notch and very low depth, right? I'm only going about 8 dB, just enough to kind of shave off the top of that peak. And essentially, that's exactly what you're doing. You're just taking this peak and you're just shaving it off so that you're just shaping that response, that frequency response, to get a nice, one-to-one response all the way out till when it starts to drop off because of its natural drop off in response at the higher frequencies. So this is kind of a really great way to, again, I will caveat this is that, this is for one configuration of your aircraft. When I mean by configuration, probably it's like more like weight, right? You go to a different gross weight, or you go to a different rotor speed, this may shift some. And so I'm not going to say it's going to be like night and day, but it could modify a little bit that you're going to see some response because the notch is so wide. It's probably not going to be a huge deal, but be careful if you're making large weight changes that you're going to change this rigid, what we call a rigid body mode. That frequency of which it's oscillating at could change. So be careful on that. All right, position controller system ID. I had done some research last year. I've been doing research in handling qualities for to call like where the autopilot's in control. We're calling that automation qualities, right? How good is the autopilot controlling the aircraft, and how can we measure the goodness of the autopilot controlling the aircraft? And so my research looked at a number of different metrics that we had to measure through doing frequency sweeps in the position controller loops. And so, and again, this was done this is not only helicopters, this is also multi-rotors. My colleague and I did testing on 2 multi-rotors and 1 helicopter for this research. And so with the metrics we're looking at, and I'll explain some of them briefly, is tracking bandwidth, there's velocity bandwidth, and then position disturbance rejection bandwidth, and velocity disturbance to rejection bandwidth. And to the right here is kind of showing the Bode plot, or the magnitude or gain in phase for tracking bandwidth and how it's determined. And basically, you're looking at the position of the aircraft, right? The actual position compared to what the target position was. And so then you're sweeping that and looking at that over frequency, right, on the x-axis. And I'll just look at the position one, the velocity target or P to velocity targets similar, but let's just talk about the position one. We can calculate in one of two ways, and this is one of them. So what we say is that when the phase between the actual target and the actual position and the target position gets 45 degrees out, that's kind of the key frequency that we say that that's the bandwidth. You can vary the position up to that frequency, and the aircraft will still stay with it up to that frequency. Beyond that, you're going to see a lot more phase loss, and it's going to be poorer performance. But that's kind of what we determine as we call bandwidth, right? It's up to a certain frequency that you get good response from the aircraft and keep it within phase. So like I said, we through our research, we determined that tracking and velocity bandwidth were key criteria to demonstrating good automation qualities. So I made a PR and it got it merged. Basically, the position controller system ID now has these sit axis options that allow you to then sweep on both measured position, measured velocity, and then input velocity as well. And again, the frequencies, the axes are by body referenced, so that it gives you a lateral input or it gives you a longitudinal input relative to the body. You got to remember the position controller is Earth axis referenced, and so we basically did the transformation to make it body axis referenced, because most aircraft, especially helicopters, have different responses in the different axes, although the position controller tries to make those be the same in the way you tune it. So there you go. We have those 6 different new ways of using the system ID. One of the things to remember is that when you go into system ID mode with one of these axis settings, you no longer have control of the aircraft, right? It will stay in one position and it will do the frequency sweep on its own and your inputs will not matter. So if for some reason the aircraft goes unstable, switch out of the mode, right? Go to stabilized mode, go to alt hold, get out of a position stabilized mode. Don't go to loiter. Just get out of that completely and recover the aircraft, and then figure out why you got some sort of divergent response. Most likely it's going to be your outer loop tune, or maybe even your inner loop tune. The other thing about this is since you're looking at position, right? You're going to and GPS is probably not going to have a high enough accuracy. You're going to need to use RTK, real-time kinematic, to allow you to get to accuracies below 5 centimeters. Probably 3 centimeters would be really nice, and that way you get, because look at my magnitudes I'm asking for are 30 centimeters, right? You don't want to go much more than 30 centimeters. The aircraft's going to get too high of bank angles, and it's going to be the response is not going to be very good. And the data probably would be somewhat tainted as well. So really only 30 centimeters is probably enough. You could probably go to 10 or 15 centimeters and you'd still be good and have that sweep. But that's why you need that RTK accuracy when you're doing it. Again, for the position controller, right, much different than the attitude controller. So there's frequencies are much lower. That you can the bandwidths that you can control at are much lower. So your start frequency and end frequency is significantly lower than what you'd use an attitude controller. So 0.08 hertz. If you're looking for position disturbance rejection bandwidth, you might have to go lower than that in order to capture it. No more than 2 hertz really for the upper frequency to capture the velocity and position bandwidth or tracking bandwidth. And again, with those lower frequencies, you definitely want to have longer sweep times to capture enough data to do the analysis. All right, so these, I'll kind of let you all, I think getting short on time, I'll let you all kind of look through that on your own. But the next few slides basically show the position controller here in the inside here. This is there's the aircraft bare airframe. Here's the attitude controller. There's the loops that are wrapped there. And then outside of that is basically the velocity feedback and the position feedback and how the position controller works. Out here is where the waypoint navigation and trajectory generator, so basically shaping happens. And so basically, we're basically looking at inside here from the velocity desired to position desired for tracking bandwidth or for velocity bandwidth. And then for the disturbance rejection bandwidth, you're basically kind of taking the forward loops out of the picture and you're just looking at how it responds to disturbances. And we're basically adding a disturbance here as the measure position, just kind of adding that disturbance in there. And then we're using what comes out to do the analysis. And that's for position disturbance rejection bandwidth. And then for velocity disturbance rejection bandwidth is the same idea, except on the velocity loops. Um, questions on that? Uh, Nate. Yep.
Um, I guess what you're describing is a robust control, right? In a sense, or wouldn't you?
I'm describing a way to determine how robust your control is.
Okay.
So it's essentially the guidance given by ADS 33 is basically providing you ways to generate metrics or has metrics to basically see how good and then be able to bounce it off of a specification to say, how does it compare to the manned specification? And we actually go into further detail to talk about how can you scale that for unmanned aircraft that are much smaller than the manned aircraft? Because obviously the dynamics of a full-scale manned aircraft are going to be much different than the dynamics of a model scale autonomous aircraft. And so we go into how you would scale that.
Okay. And then a silly question, but how did you draw your control diagram here? Like
Oh,
what software?
I just used it was done PowerPoint.
PowerPoint? Okay.
Yeah.
It looks quite nice.
Okay. Thank you. Oh, for injecting measurement, artificial measurement errors. Yes. So basically, the chirp is going in. The VD in is basically where the chirp signal is going in and added to the measured velocity to then make the aircraft think that it's seeing a disturbance and then seeing how it responds to that to then be able to determine how the goodness of its disturbance rejection. No, you only put it on the position loop. So you don't put any velocity disturbances there as well. It's just on the position loop. Yep. Yep. All right. To wrap it up, future work in traditional helicopter stuff. So like I said, auto rotation's kind of been a big push at this point. I know Ferruccio and Matt are probably going to be looking at this engine failure detection for automatic transition to assisted auto rotation. Pie in the sky, big goal like is at some point going to autonomous auto rotation. And I say, and they're going to explain what they mean by assisted auto rotation. Essentially, the pilot is still in the loop, directing the aircraft laterally, but the autopilot has the collective and forward speed control. And so autonomous would be it's taking full control. It's going to guide itself to a point to land. And so that's kind of the pie in the sky where we would like to go with that. Some other stuff that Matt and I were talking about was ability to change head speed, target, and flight. Right now, we're kind of dictated to just one head speed. And I know there's a lot of, in order to get better performance, there'd be the desire to reduce head speed in flight in order to gain better performance. And even gain scheduling based on head speed. And then lastly, I had a lot of users that fly these smaller helicopters that have essentially fixed pitch blades, and so they want to do variable pitch, but can do some tilting of the tip path plane, so they can do not cyclic, but basically tilt the thrust vector, and then they want to be able to basically have the thrust changes based on RPM, and I think that might be something we could probably do fairly easily and provide some thrust linearization in there to help it out, so that it's not so non-linear with throttle. So that's all I got. Any questions? Any other questions?
Going back to the SysID on position, you mentioned that you'd set the max, or your recommendation was to set the max sys magnitude for like 30 centimeters because of concerns over sort of potentially pollution of the data. Can you?
No. So basically, you're kind of yeah, you're drawing a fine line between potentially hitting some nonlinearities in the position in the attitude controller and the position, because as you command larger movement of the vehicle, it's going to respond quite aggressively, and you're going to get larger attitudes. You could almost even hit the attitude limit of 30 degrees if you set your attitude limit 30 degrees. So you want to keep those displacements smaller, just enough so you have enough. I don't think noise was really ever an issue with the position controller. So you want to keep them large enough that you have good signal to noise, but not so large that you're getting like at the peak of where it's really starting to respond. You're not getting much more than 10 to 15 degrees of attitude changes out of it.
So just my follow-on question to that then is, because you're trying to assess the robustness of your automated handling qualities. If we've done it within that linear region, what about beyond? What if the vehicle does genuinely get pushed into those nonlinear regions?
I mean, the spec really doesn't address that, and kind of what we're doing with even the criteria is kind of basing upon the fact that you're kind of maintaining some linearity.
Okay, thank you very much.
I can potentially address that a little bit. When we get saturation or we hit those limits, the controllers are designed to recover elegantly from those saturated states. So when you get larger and larger limits, you simply get to a point where the controller is saying, okay, I'm now doing everything I can to move back to my target set point. And then once we get back to that linear position, we want to ensure that that last 30 centimeters is recovered elegantly. That's where all the fast response time comes in. If you drag something off 10 meters, it's just going to reach its maximum speed, wait till it gets back to within that 25 centimeters, and then we get back to what Bill has characterized in how fast and elegantly we hit the spot.
Yeah, well, just remember that the position controller ID, are you saying that we're including this shaping or not including shaping?
No, I'm saying in what you're characterizing is that last fast response thing. Once we get into saturation, it's higher levels of the controller that deals with that saturation to ensure that happens elegantly, and we come out of that saturation elegantly and back into this linear stage, linear region where you're characterizing.
Ultimately, you want to stay out of that area, but again, that's where you have to kind of really assess kind of how much attitude are you getting out of the change and distance you're requesting.
That's the key reason why Bill's saying you have to keep these inputs small, is because we will hit that quite quickly.
And then a shameless plug, at the bottom of that one slide is the reference for the paper that my colleague, Dr. Ivler, and I had published this past year on this research. Any questions? Thank you.